So this talk is the next generation of extensible effects library. It was presented at Haskell Symposium 2 years ago. But I also want to think about as the last generation of the extensible effects library. So, well, free monad, they've always been elegant, and now they're extensible, and finally now they're efficient. So my claim is there is no reason to use anything else. And the rest of the talk is actually should be, in the rest of the paper, the second line should have been more over extensible effects. So the paper shows some applications of extensible effect libraries. For example, non-deterministic committed choice, catching IO exceptions in monads, well, other than IO actually in the presence of any other, and the regions. So all of those applications have already been implemented before with varying degrees of success. Well, the second item was actually had the least degrees of success because it was quite unsatisfactory. And now they're all implemented with extensible effects. And my claim is, well, they're uniformly more successful and actually, they're fast and elegant. But I don't think I will have any time explaining this part. So the paper is the start with introducing extensible effect and how extensible effect arises. And in the talk, I want to concentrate on this first part, how you can think about extensible effects and how you can think about free monads. And not only how can you think about, how can you derive them automatically. And so I use this quote misattributed to Michelangelo that we just get removing surplus. And so I will show how all this approach emerges. If we start with the most straightforward implementation we can start to think of and just remove this boilerplate and extra parts until we get to the end. Okay, so we start with the simplest thing we can think of is that, well, we're interested in the simplest effect, which is a reader effect or dynamic binding, right? And so here are the specification of effects. So it's a computation that has no effect whatsoever, pure A, which means that it works silently towards some value of A, or it's a computation that says cannot work silently, it says it needs some value of type I, and if it gets this value, then it continues and maybe asks some other values, and then eventually it returns A, well, if it doesn't diverge. So this specification was pioneered by John Hughes back in 1995, I think, in a paper on deriving pretty printers, and Ralph Kinsey in 2000. So it had excellent introduction of this style of deriving. So you give algebraic specification of what you want, and then you specify it. So I try to follow exactly this point. So, well, now we'll get this data type that describes computation that may perform side effect, and here is one of the computation that does perform side effect. It simply asks the value from the dynamic variable, immediately returns it. Well, this is the simplest one, but we want to have something bigger, and to get something bigger, we need a way of combining something. And to combine, well, the combining things is a monad, right? So that's how we usually combine effective computations, and here's the bind operations for monads. And I will be using this function, which is a classical composition, but you can think about it as, well, it's a composition of function, but with m tucked inside. Or if you prefer, it's a call by value function composition. Okay, so now we have monads. Now we can really write something. For example, this function addGet takes a value from the environment, takes a value as an argument, sums them together, and returns. And here's another thing. It takes n values from the environment and sums them up and returns. So it's very easy, so we can write those up. And of course we can, well, these are just specification of the computations, right? So what we wrote before, they don't actually do anything. They, ask for something. Now we need to interpret them. So here's the run function of this monad. It's run reader, so if the computation says doesn't need anything, here's the value, then it returns, and the computation says, well, I need a value, and then I can continue, then it just gives it the value. So it's a standard implementation of reader effects. Well, looks exactly the same or feels exactly the same as Haskell Reader, but it's actually more flexible than Haskell Reader because we can write a different interpreter, for example. This one. So reader interpreter takes one value, and whenever it's asked, it just gives us exactly the same value to this computation. But here it takes an array of values, and whenever it's asked, it gives it the next value. So now it looks like a stream of values, and it looks like this addGet or get. It looks at a parser combinator. And we can build parser combinators libraries. And the name IT is actually meant for iterative, and it's actually enumerator. But anyway, so I hope that you realize it by now. Okay, so that was good, but we might want to not only read, but we want to write. And here we add another effect. We want to put something. Well, then we add put operation, so this operation can read and can write and can do nothing and just return. And of course, we can write monad instance for it, and we can write an interpreter for it, and then, so forth, so forth. So then we know what to do. But there is something wrong with this picture. There are several things to do wrong. Well, look at this IT is small with only pure and get, and this one with pure get and put. I mean, this part, exactly this, well, kind of feels the same, although the type's a little bit different, right? So when we add a new put effect, we don't want to rewrite. So now we had to rewrite all these previous things, right? We want to just add this new data type. Well, unfortunately, data types in Haskell are not extensible. In ACaml, by the way, they are, but in Haskell, they are not. So we have to rewrite this. So that's the first thing. Then look at the interpreter. So this line of the interpreter, that's the one that actually handles the read effect. It's exactly the same, this line in the interpreter reader-writer that handles read and write effect. Right? Again, we don't want to actually keep rewriting our interpreters because we just add some more effect if they don't interact. Well, unfortunately, functions are not extensible either, so we're stuck in there, keep rewriting. And the third thing that is here, well, suppose we want to have computation that, well, we can write the effect with tells, which takes a value and immediately tells it. And here are the computation that gets something and immediately tells it. And it would be nice if we could reuse this function at get from the previous slides, but we can't because it has wrong type, right? So now this one has IT capital, and this our get had IT small capital, so it's a wrong function. So the code is actually exactly the same, but the signature is different. So that's another thing that's, well, since monads were introduced, almost the beginning, people recognize they don't actually compose. So if you have one program written using one effect, another program using second effect, then we try to put them together. Like in here, we're just stuck. So that's lack of extensibility. Well, we know about it, but for 10 minutes, I'll be talking about different problems here. Let's look again at this monad instance for ITIO. Well, these are two things look almost the same, right? And the meaning is actually very similar. So what does it mean if we have a computation that asks something and says, well, after you get what you want and return some value, then here's how you should continue. And the bind instance says, okay, you get something and continue as a composition as k prime and k star. So, if you have two ways, do k prime and then do k, well, that says do k prime and then do k. And put instance says exactly the same. And if we have more effect, that would have more instances, and we'll have look exactly the same. So this kind of unsatisfactory, so why we keep writing exactly the same thing? Can we factor out this common thing? And that's what exactly free monad do. So that's the definition of free monad. Now we have a single impure, and f is a star-to-star type constructor, which meant to be a functor. And now we write, if f is a functor, we write this single monad instance. And all this boilerplate is factored out, and there was one single instance. There is no more, there is nothing more in here. This is finished. So before we had this part, and now we write only this part for reader-writer, right? So there is no need to write any instances monad because there is only one instance of a free monad once and forever. So if we want to have new effects, then, well, we define this signature for new effects and define the functor instance, and here it is, our free monad. So that's all. But there is some boilerplates a little bit. So let's look again at this monad-free instance. fmap, and it's meant to, this single line meant to be representing these lines and all those lines, so forth, so forth. And what do they do? What actually this fmap does? Well, it does what, here. So if we take this k, which means if you do some effect and eventually return something, then, after that, you should do k. And in all of those effects in F, there may be some here encoded. Well, if you get some value, what you ask for, that's how you should continue. So there is always some kind of k prime buried in that. And that's what fmap tries to add to this k prime further and further. It tries to grow the continuation. So there's also a boilerplate that if fmap kind of tries to find a buried continuation and add to it, try to find a buried continuation. Well, it's kind of natural to think, why if fmap spends so much time finding this buried continuation, just unbury this continuation and make it explicit. And that's what we get. So this is free, and this is freer monad. So this is continuation which was buried somewhere inside F. Now it is explicit in here. And so what's the advantage of it? So that was the definition of free monad. It's also a monad. And now if we have this K prime, now it's explicit, we just add this to here. There is no point of groping in the data structure, finding where it is. It's right there, right? And, I mean, the reason is there are no constraints. There's no functor constraints because we don't need it. All the functors were needed doing, now it's done explicitly. Okay, so here's how we write reader and writer monad in this way. So reader writer, so we have get and put. So when we define get and put, we don't need to define any continuations anymore. Like get request doesn't have any argument. It's just say, well, get it. It's my action, and that's how we define. Okay. Because it's such an important thing, let me show you the different way of looking at it, more theoretical way of looking at it. So if we have a f and it's a functor, then we can write a functor instance for it. And if we have a g which is not a functor, well, obviously we cannot write functor instance for it. But we can cheat. So g is not a functor, and so we cannot write a functor instance for it. But suppose we can put gx with some kind of, if we say we want to map x to a, then we just put this x to a into a data structure. So when we say f map something to data structure, we don't actually do any f mapping. We just keep this x, our mapping function and this data structure separately and packed into there. And all of a sudden they are functor. So now, if we can write a functor instance because if we have mapped something more, we just add this something more to the one that mapping function was already. And well, this is a left con extension. And our free monad is actually, this is the equation that defines it. It's a left con extension of this original monad. So that's why the functor constraint disappears. So truly speaking that, well, freer monad is a very cute, freer monad is a cute term, but generally speaking, categorically, they're both free monad in a categorical sense that it's a left adjoint or forgetful operation. But they forget different things. So the classical free monad forgets bind and return. And this free monad construction remembers this or gives the standard implementation of bind and return. And the free monad forgets even f map. So you don't even need to bother with a functor instance. You get it for free. And of course, you get applicative and other instance for free. So now in a free monad, you just concentrate on what, actions you perform and forget about all the boilerplates. Okay. But there is a performance problem with a free monad, which is well known. So if you look again at this, and a free monad at this formulation actually becomes much more closer. If you look at this definition and we look at the instance, well, we see that what happens with a bind. So it's kind of operation left association, where left it traverses the left argument, but it keeps this right argument k passing along. So it looks exactly as list concatenation, right? So it has to look through the left argument, but keeps the right argument along. And we already had presentation ICFP, well, this year and Haskell Symposium last year, why this is a problem. So yes, and that's exactly the problem. It's algorithmical performance problem, but it can be fixed. Well, if you, we saw 2 days ago, we just use some kind of better data structure. And I already had a comment as to what the data structure is, and I don't have much time of describing it. So this is more efficient data structure, which represents this continuation that gets x and returns some argument. So how does it work? It kind of does similar things to this. So this operation and this operation are kind of very similar. But this operation is a function composition, right? We saw the definition. It really composes the function. And this is also like a function composition, but it doesn't actually compose function. So it gets to structures to functions, just puts them together. So it's the same idea of left con extension. So don't actually do any operation, just accumulate them, think in the hope that you don't actually need to compose. And that's exactly our hope actually satisfied. We don't actually need to compose this continuation because we're going to break them anyway. So that's the moral of the story is that, be lazy and don't try to do more stuff that you needed. Just pretend that you've done. Well, of course, we need to at the beginning, I talk a lot about extensibility problem, that how we, we cannot add to the data type, we cannot add to the handlers, and so forth. But that's a more or less solved problem, and in Haskell 2000 or 2 years ago, that was a solution. So we just have to use open unions. And if you use, put this open union in here, then you, solve the problem. So that's the end result. So this is the extensible and free monad. It has open union, and this is one single instance for it. And this is an example how we're going to use it. That's exactly reader and writer. So we have reader monad. Now we define this one effect, get. And we have operation ask, which sends effect get, and has operation run reader. That's how it implements it. So it says if you get a k, get effect, then it just passes this I to this continuation and continue. And if you have a writer effect, then you can write tell, and you can run writer. And run writer, of course, only handles about put effects. It doesn't care about other effects that could be done. And you can have a computation that has both tell and has this original add-n, which remains as it was. And we can compose them. And if we're going to write, then we run reader and writer. Or we can, in this case, because they're commutative, then we can put run writer and first and run reader is later. So, either way, it actually works. So, okay, so about performance. Because that's the biggest thing, but, well, the slide is empty, not because I don't have any graphs, actually. I have too many graphs. And I always don't like to put graphs on the slides, because if I actually care about it, then there is not enough time looking at it. If I don't care, then, why I'm looking at it. So, so this is the only one, line that you should remember. So if you have a single state, yes, single state is much better than this extensible effect, or probably anything else, by a factor of 30. Which is actually good, because originally it was 2 orders of magnitude, so now it gets reduced to the factor of 30. But if you have a single error monad, the performance is the same. So this extensible effect and error monads are the same performance. It's only for state. And the reason for state, because GHC has a specific optimizations tuned to the state monad. But once you start some layers to the state monad, even one layer, then the performance is on par. And then you can see from the graph there is algorithmic improvement. So if you add layers and state monad becomes quadratic, then freer monad is linear. And when state monad is linear, then this monad is constant. So it's algorithmically, and it's also not only algorithmically, constant, also smaller. So it's in all respects, it's this. So if you have one single state monad, yes, currently it's not yet, done. But if, well, GHC, pending GHC support maybe. But for other cases, just use that. Okay, that's just a small slide about something that I'm not going to tell, that there is also implementation of monadic regions and fluid Morissette, and by accident it was also, original regions were also presented in British Columbia 7 years ago. So in Victoria. So this is kind of continuation of that work. And it was implementation in Haskell. This is different implementation of extensible effects. And I think this new implementation is closer in spirit to the Fluids and Morissette paper. So without the iterating monad transformers. There is no monad transformers anymore. Okay, so this is the, I'm almost at the end of my time. So this is the, again, last slide. This is the monad, which is extensible effects. It's extensible, freer, and it's performant monad. And here is the conclusion. So that's what I'm going to say. So there should be no more monads. So I think this monad is the only one monad that should be. We write this only one single instance of monad and never bother even writing any more instances. And specifically, we never bother writing any more tutorials. Thank you.
Just a quick question. I didn't have enough time to comprehend your slide, but your free data type signature seems to be very close to the operation monad time signature.
Yeah, yes. And there is a thing about in the paper, yes.
Yes. Then I can read about it. Thank you.
So that was a nice talk. There seem to be some similarities with work we did 2 years ago.
Yes. And you can read the paper about this.
So your notion of freer monad is pretty much exactly what we implemented.
Well, yes, and there was a discussion in the paper that, well, one of the things that you still have some constraints, right? So in your, if you look at the code, then you still have, yeah, it has to have some constraint, and I think it has to be interpretable, right?
No.
It has constraint. I mean, you know, at least in the figure on the paper, there is a constraint. It has to be interpretable, right? It doesn't.
We should look into this.
Yeah, I can show you. So the reason in here, there are absolutely no constraints. So it's a free monad. I mean, there are no constraints, no type classes, whatever f you give it to it, it's always a monad.
Okay, but the basic idea of pulling...
Oh, yes, the basic idea, yes, but the basic idea is not, I mean, yours. I mean, the basic idea, as you just said, it's operational, and before it was Unimore. So the basic idea, yes, I mean, but you are not the first to invent it.
No, of course, it's well known.
Yes, so.
The other point I wanted to make was this business of just having a single state.
Yeah.
Our library, we lose no performance in that case.
But, I mean, but also, yes, you can.
And it's taking advantage of, well, sort of accidentally taking advantage of fusion in Haskell by restricting the way in which you write your handlers for these effects. So that if it's always a fold, then you can get very efficient performance in that case.
Yeah, I know that, but...
And Tom Trivers has a very nice paper about this.
Yes, I know that work too. But again, I mean, we're talking about one specific optimization, right? And the reason state monad actually works, because there is an optimization as GHC, right? So strictly speaking. So we can also say if we are going to in the business of putting optimization as GHC to specialize some state monad, then we can probably do some optimizations for the free monad as well.
Well, I think the other big advantage is if you restrict yourself to a fold, then you're guaranteed to get much better performance than in the more general case that you provide. Okay. So it might be interesting if you could have some way of detecting when there is a fold.
Yeah, I agree.
Yeah. Okay. Thanks.